Hi, in this video, we'll discuss on the topic code optimization. Why do we need to optimize the code generated by the compiler or the intermediate code which is generated during the compilation process? We have a study which shows that there are certain requirements for optimization in order to improve the execution time of the program. The golden rules of optimization, which means if you study which were taken for analyzing the execution time of a program based on various instructions, has told us something about the time required for executing a certain set of instructions. Now if we could concentrate on those instructions, then the execution time of the program can be reduced to a larger extent. The first rule is the 80-20 rule. 80% of the program's execution time is spent mostly on 20% of the code and not the overall code. So now we are supposed to sort out methods where we can improve those 20% of the code. And another study says for a performance hungry program, 10% of the program has to undergo optimization, because that is the one which eats away 90% of the execution time. And what is this all 10-20% about? It is mostly on the execution of the loops which we have in our program. So now spending our time to optimize either the 20% or the 10% of the code, or in general a minimum portion of the code, will help us to improve the execution time of a program. Now, where does this code optimization occur? We all know the first phase of the compiler is lexical analysis, and then syntax analysis. We do a semantic analysis and also generate an intermediate code. Now all these phases have link with the symbol table, because they have to know what the identifiers are, to which data type are they assigned to, and so on and so forth. And therefore we have to know of how this code optimization symbol table works out. The next one is the code optimizer. Code optimizer, mostly they work with the intermediate code, and sometimes they work with the code generation phase also. Now this code optimization phase is an optional phase. Certain compilers the code optimization phase is built in during in the compilation process itself. For certain other compilers, this code optimization phase is given as an option. So if I could add that option while I compile it, then you can optimize your code. Normally when you do compile a program for your C++ program, we in our Unix platform, we say GCC minus C. That is how we compile it. If I just have to compile it, then I'll say GCC minus C sample.cpp. Now if I have to optimize the code, then I'll say I'll have an option as O. So it is GCC minus O sample.cpp, which will now optimize your code. Earlier it just compiles, does a lexical analysis, syntax analysis, semantic analysis, and try to convert the given program in an object code, and that's it. It doesn't go for execution. But then now what we do, we also try to optimize it. So you have an optimization part also. Now there are various levels when you try to do code optimization. The first one is a local optimization. We just select a region of the code, because the program might run for in the lines together. So we try to do an analysis on the region of the code, which we call it as a window, and such type of optimization we call it as a peephole optimization. The next one, to understand the procedural flow or the flow of the program and to identify certain local regions, we should understand something called as basic block. So the first few slides we will try to understand how you divide a program into few basic blocks, which will help you to optimize it further. and then the global optimization based on the control flow and based on the interdependence graph also. So we'll mainly concentrate on how a basic block is been built or identified, and then how we do an analysis. Then we'll try to go work on the peephole optimization and also the loop optimization part. Moving on, what is basic block? Basic block is a sequence of continuous 3 address instructions. Now if I can group a set of basic blocks in terms of say basic block 1, after basic block 1 basic block 2 will be executed, so on and so forth. That flow we call it as the flow graph. So you have two terminologies. One is the basic block and the other one is the flow graph. Now let us take an program code snippet. Try to identify how you divide those instructions into basic blocks and how you do it as a flow graph. So coming on to the example, now what do I have here is a 2-dimensional array which we are setting it to 0, and then all the diagonal elements we are making it to 1.0 1. So we have an array at the end, 2-dimensional array, where the diagonal elements alone is 1, the rest of the values are 0. Now when I try to convert this into an 3-address code, these maybe 5 lines of code gets converted to 17 instructions. We'll start with, first let me initialize I to be 1 for this for loop, the outer for loop. Second time let me take j and initialize it. Now if I have to take j, in every row there are 10 values. That is how it works out. It is a of 10 comma 10. So every row is indicated by I and every row has 10 values, and therefore now I have to take this 0 comma 0. If it is 0 comma 0, it's the base address, and if it is 0 comma 1, I have to move one step ahead, so on and so forth. So I have to do a lot of mathematical stuff in calculating the correct offset value, and that is what is done here. So it is 10 star I, every I contains 10 values, and then you say t1 plus j. If it is 0 comma 0, it is the first value, is 1 comma 1, it is the first value. If it is 1 comma 2, it is the second value. If it is 2 comma 1, then it becomes the next value. So you take it as 10 star I, then you add the value of j to it, and then every value has allotted by 8 bits. So what I do here is I multiply into 8, and then I subtract it just to get the correct offset value for 88. And then now I know I have a of t4, which is 0.0. This is where I do this. Now what happens? For loop increments j value and I value by itself. Now we are supposed to increment the j value, and then I have to check if it has exceeded 10. In that case, if it is exceeded 10, it should go to the outer for loop, or it should execute the same for loop again. So that is where we are checking if j is less than or equal to 10, it goes to 3, the inner loop. Then once this is done, if this condition is not true, that is you have met all the 10 values in a row, then you increment I value, check if I is less than 10. If so, I have to again re-initialize j to 1, and therefore I say j is equal to 1. And then this part is over. So this 3 lines we have made it into 11 lines, and then here again we'll take I, we'll do some modifications, and then we'll assign the value. We'll add I equal to I plus 1, check it. If so, it moves to 13, and this gets repeated. Now this is just an change of your normal high level language code into a 3-address code. So now what am I supposed to do? We are supposed to identify the basic blocks. Basic block has one term called as leader. Every basic block will have one leader. Now we are supposed to identify who the leaders are. So we'll just take the example, and then we'll move on to the algorithms. Now we'll identify the first instruction would be a leader. The first instruction in the program would be a leader, and hence you have I equal to 1 as a leader. And then you have the next instruction, which is the point at which you have the entry point of an goto function. Now you have an if condition here, it goes to 3. So this 3 becomes another leader. The entry and exit of a loop will be considered as two different leaders. So now when I say this goes sequentially, so first I can mark this as a leader. We just move on checking for leaders. There are no other if conditions. And when it comes to 9, the if condition here, it goes to the point 3. So 3 becomes a leader, and then you move on, and then you go ahead with go to 2, and 2 becomes another leader. Now this is the output of it. So now t is equal to 5. What is it? Now we are not talking about the exit position. Now t is equal to 5 is the instruction which starts another loop, or in other ways you just move ahead and then you say this 13 goes to this point. So then based on the next condition, you say all the entry point, wherever go to points to, all those are considered as leaders. So 3 becomes a leader, 2 becomes a leader, 13 becomes a leader. Now the exit point of the condition. So I equal to I plus 1 becomes another leader, I equal to 1 becomes another leader, and that's it. Now we'll talk about the basic blocks. So now what happens? A becomes a basic block because it's one leader, and the next continuous instruction is a leader again. So I cannot make it as a basic block. Now B becomes another basic block. Now what about including 3? 3 is another leader. So B stands alone. Instruction 2 stands alone. And then 3. All this put together is a basic block C. And then for basic block 4, you have 10 and 11. Here they have taken it as D. And E stands separately because the next continuous instruction is a leader. And from 13 to 17, it is another basic block. This is how we identify the basic block. So the first step of identifying the basic block is to identify the leader. To be concise, the first instruction is a leader. The entry point of a goto function is a leader. The exit, the next instruction of a goto function is a leader. Now that is what is said in the algorithm here. First instruction in the code is a leader. Any instruction that is a target, that is wherever the goto jumps onto, that becomes a leader. And any instruction that immediately follows the conditional statement, the goto statement, is a leader. Now identify the leader and add as many as other instructions into the basic block, and when the next leader comes in, it becomes a new basic block. So that is how we identify the basic block. So this is all about identifying the basic blocks. Now we'll move on to the control graph. This is what you call it as the flow graph. Now what really has happened is we move on to the entry point. B1 is the first basic block, that is A basic block, and then from there we have and move to B2, and then you have it as B3. Now there is a small change between these statements here. So now what happens? It goes to 3. So you have to have a loop from the 9th instruction, that is the exit point of the basic block, to the entry of the basic block. So now I'll have two outputs. One is it moves, if this condition is false, it moves on to basic block 4. If this condition is true, there is a cycle here. And again, if this condition is false, it moves to basic block 5, and here you have a condition. The same way, and then you have the exit. Now we have to identify the loops. How do I identify the loop? This is a sequential flow, whereas these are the loops what you have here. So there will be a loop entry, that is what they say. Now how does it happen? This B3 is a loop. There is only one basic block in it. So you have a loop with set basic block B3. Now similarly B6, you have a loop. You have an entry and you have an exit point. So there it is B6, but you just talk about B4. B4 goes on to B2. So in this particular outer loop, you have three basic blocks, B2, B3 and B4. That is how it works on. So this is how I try to identify the loops. Once we try to identify the loops, then you make an analysis of what instructions can be reduced or what instructions can be moved away, pushed away. So there are many techniques which we will learn it one by one. Now we'll talk about the local optimizations. What transformations can we make in an basic block? The first one is the common sub-expression elimination. Now what is common sub-expression elimination? To identify all this, we have to know something about the next use information. So that is what you call it as an next use information, and next use information, how is it defined, and then you go ahead with the basic blocks. So now what is this next use information? In very simple terms, suppose I have two instructions, A equal to B plus C, and there is another instruction somewhere down the lane. Maybe I say instruction 2 talks about computing the value of A, that is A equal to B plus C. And the other instruction, maybe instruction 5, uses this A value and say add of A comma B is equal, C is equal to add of A comma B. Now what happens? The value of A which we have computed in the second instruction is used in the fifth instruction. So that is the next use information. What is the next use information of A? That is used in the fifth instruction. If you talk in terms of basic block, they say basic block 1 has defined A, maybe basic block 2 has used the A which I have defined in basic block 1. So this A value has to be retained in the register as much as possible till you say that there is no more use for the variable A. So that is what they use here. If X is computed, X is any variable which is computed in a generalized statement value of I. In our example, we took it as 2. And is an operand of A. In example, we took it as the fifth instruction. And if J is greater than 5, its value must be preserved in the register until that statement will be executed. If X is computed at K and K is greater than I, the value computed at I has no further use. So now X is computed at K and you use it at I. And after that you don't use it at all. So now what happens? This value computed at I has no further use, which means it will not be used in a program. Sometimes we also do some calculation of certain variables in our program by mistake. And when we compile it, our compiler will not give an error. Rather, it gives us an warning message saying that the variable which was defined is not used at all. Such kind of user-friendly messages we get. So now what do you do? Then you try to find out that variable is of no use. Sometimes we delete it, sometimes we stop it there. Now this information is also can be used for garbage collection, where the system sweeps the information from the memory also. So that is how a next use information is evaluated. So for the next use information, there are certain definitions. Statement I assigns a value to X, J has an operand, and the control flow from I to J has no intervening assignments to X, which means once I have defined X in ith statement, the in between I and J, that is in between instruction 2 and instruction 5, nowhere down the lane X value has been modified. But then value of X is used in statement J. In that case, X is alive or X lives in statement I. It has been defined in statement I and it is used further. So that is how you go ahead with the next use information. So there are certain basic level optimizations which we have to take care of. The first one is the common sub-expression elimination. Now we'll just take an example of A of I plus 1 is equal to B of I plus 1. Now what do I do here? I have to have know the value of I plus 1. So easy way of converting, T1 is equal to I plus 1 and B of T1 will be assigned to T2 because this has to be assigned to a temporary variable, and then it is I plus 1 again. I am not doing any code optimization. So what do? I evaluate I plus 1 again. So between I plus 1 is evaluated, stored in T3, and then A of T3 has to be assigned with the value of T2. Now among these 4 instructions, I plus 1 is evaluated in T1 as well as in T3. Now if you see, in between the first instruction and the third instruction, I value is not modified at all, which means T1 value and T3's value will always be the same. So now this is a common sub-expression. So this expression can be eliminated, and therefore we'll just go ahead with T1 equal to I plus 1, T2 is equal to B of T1, and A of T1 is equal to T2. So such kind of common sub-expressions can be eliminated. The next one is constant propagation. What do you mean by constant propagation? Suppose you assign an identifier with a constant value, and wherever you use the identifier, this constant value alone is there. There is not much of any changes onto it. So such kind of example is taken. So in the previous case we'll take a T of I plus 1, this part alone. I say that I equal to 4. It's not into a for loop now. It's just saying I value is 4. So now what happens? You do an assignment of I value with 4. Then you add the I value, so on and so forth. So now since I value is not going to change in the program, I'll take I as 4, and T1, instead of doing an addition, it performs it and says T1 is equal to 5. Now you do an addition. Now what happens here? I value is 4, T1 is 5. Here instead of taking 5 and doing all the modifications, I'll insert 5 here. So I am just step by step, I am removing all the variable assignments with the numerical values. And now my final code would be I equal to T4. Now if I assign 5 here instead of T1, T1 is of no use. So I'll take I equal to 4. Maybe that's required in the program. And then T is equal to B of 5 and A of 5 equal to T2. So now what has happened? I have reduced an addition to just a copy statement. And then doing all the modifications, I have also removed this copy statement. So one addition with one copy statement has been removed. Taking these values, assigning itself also has been removed. It is all within constant value. So that is how you do a constant propagation. Then you have optimizations on context-free grammar. We'll see how it works on. You have common sub-expression elimination, constant propagation. There is partial redundancy elimination, dead code elimination, and so on. Now we'll see redundant expressions. Redundant expressions is similar to our common sub-expression. So if you see here, you have m is equal to a value which says t0 is equal to 2 star I, m is equal to t0 star z, and then t1 will be 3 star y and t1 star z, and here it is 2 star y and t2 minus z. So in between t0 and t2, we haven't changed the value of y. If the value of y has been changed, then t0 and t2 will give us a different value. But here in between t0 and t2, we haven't changed the value of y. And therefore, I am eliminating t2 in the third step. And in the place of t2, t0 has been replaced. That is your redundant expression elimination. Now, how do we define it? You have certain expressions in a flow graph here, control flow graph. So now here you have c equal to a plus b and f of I is equal to a plus b. There are certain candidates. Now what do I mean by the candidate? It is all the expressions what we have here. A plus b is here, a star c is here, a plus b is already there, c star 2 is there, d star d is there, a star c is already there, I plus 1 is there. So in the except the conditional statements, all other arithmetic expressions we have taken it as the candidate. So now you say a plus b, will take candidate 1. It's defined here, and it comes over here. In between, A's value is not changed, B's value is not changed. And therefore, what can we do? We can try to eliminate, do some modifications here. Coming on to A star C. A star C has an expression here and then another expression here. But then, is it redundant? Here it is redundant. A plus B is redundant. Whereas what happens here, A star C is defined here. In between block, this block, C's value is being doubled. C by C equal to C star 2. So this A star C and this A star C will not give us the same output even though it is the same common expression based on the identifier name. So this is not redundant. Then we'll move on. So what do? I'll take A plus B, put it onto a temporary variable and assign the value to C. Here I'll do an assignment except for adding it again. So we have taken this one. What about, we'll go on with D star D. D star D is only here. So it doesn't have any common sub-expression. C star 2 is also here alone. What about I plus 1? I plus 1 occurs only once. So you had redundant expression was A plus B. All others, the candidates were ruled out. The options of finding common sub-expressions were ruled out because they were not there. In this case, it was there, but the value would change. And therefore, A plus B, I have taken it, copied to a temporary variable, and T1's value I have assigned it here. Therefore, I am removing two additions and I am reducing it to a single addition. Now, this is how the constant propagation works. B's value is 5. Here I am multiplying. So, instead of multiplying, I can do an assignment. And B's value is constant. So, I do an assignment here. And what do? Instead of assigning it to 20, I'll just take the numerical value and do it. Now, since B's value is constant, here D would be 7. There is no other case. So, I have made it as D7. And here it is, A value alone differs. So, B8 is A plus 5. Now, if you check here, when it becomes 20 greater than 5, this always holds true. There is no option that this will not be false. So, if it is false, you do an addition directly, or else you add 2 to B value, assign it to D and go ahead. So, now this condition is always true. So, what do? We delete this part. We can group all these in a single statement. Therefore, the conditional statement has been removed. I'll say B is equal to 5, C is equal to 20, D is equal to 7, and this all these things has been put in one block. Now, two things we are doing here. One is, I am doing a constant propagation. B's value was assigned wherever B variable identifier was used. So, C was become 20. Here it is 20 greater than 5. B is constant. Now, C has become constant. So, it is 20 greater than 5. We have made an assignment here. Instead of adding, we have made an assignment here. During this process of constant propagation, we found out that there is no possibility of this condition to be false. Which means, if there is any statement here, that will never be executed. Only this part will be executed. So, if such kind of statements were there in between, then we remove it, which we call it as dead code elimination. So, now we have grouped everything. This condition need not be checked at all because it's always true, and therefore, we have removed this condition also, clubbed all these 4 instructions into one single basic block. Now, there is another copy propagation. This was constant propagation. Now, I do an copy propagation. Where do I do an copy propagation? When we have statements like x is equal to y and so on, we do an copy propagation. Here it is b is equal to a. So, wherever I have b, I can replace it with a. And that is what I do here. By replacing it with a, I can remove the value of b if b is not assigned in any further cases. So, this is what you call it as copy propagation. The last one is dead code elimination. Now, what does dead code elimination do? What is this diagram all about? You have B, C value and D value. A plus B goes to C. sorry, b plus c is a, so you have b plus c, here it is a, and b minus d, it is b again, and c plus d, it is c, and b plus c. Now a new value of b and c has been obtained in these two things, so it is e. Now what are we supposed to do is we are supposed to find, based on the control flow graph, whether all these variables will be used in the next consecutive blocks. And they try to find that C and E will not leave at all, whereas A and B alone leaves. So now what happens if C and E doesn't leave, which means C and E will not be used in any further instructions. In that case, these two statements, calculating the value of C and calculating the value of D, is not necessary, and therefore it comes on only to the first two instructions, deleting these two instructions. So that is what here it happens. They say that delete any root that has no live variable. C and E is not live, so the root of E is being deleted, where this instruction gets deleted. The root of C is being deleted, and the third instruction also gets deleted, leaving us with the first two instructions. So these are certain expression transformations which can happen during optimization. In the next part of the video, we will discuss about peephole optimization and loop optimization.